Okay, g'day all and welcome to another video. So today we're going to be having a look at a bunch of bit hacks. I'll leave links down below for the sources of these. We're going to look at a total of 11 bit hacks, and they're going to start out really easy. Then we'll go into some intermediate bit hacking, and then at the end, well, things are going to get fairly interesting. Just before we get started, I want to say a big thank you to all of the Patreons for their support, and I'll be putting up the Blender files for the animations we're about to see, as well as the source code, just as a big thank you for supporting the channel. And the other thing that I want to say is pretty soon we'll be updating the store. So there's Creel merchandise down below. We're going to be switching out these original designs fairly soon. So if you'd like to grab those, just snap them up now. And pretty soon we'll have some new merchandise. Be that as it may, let's hack some bits, shall we? To set any bit of an integer to 1, all we have to do is take a 1, shift it over to the correct position, and then perform an OR operation. That's going to set whatever bit we like to 1, and it's going to leave the rest of the integer unchanged. To clear a bit in an integer, we just take a 1, we shift it over to the correct position, and then what we do is we complement it with a bitwise NOT, and we AND that result with the original integer. That way we can be guaranteed that there's a 0 in the position that we want, and the rest of our integer is unchanged. To toggle a bit in an integer, take a 1, shift it over to the position that we want to toggle, and then perform the XOR operation. We'll end up with a result which has the same bit pattern as before, except that single bit is flipped. This next bit hack converts trailing zeros to 1. Trailing zeros are any zeros on the very right hand side before there's an occurrence of a bit which is set to 1. And what we do here is we subtract 1 from our number, and then we OR that result with our original number. This next bit hack takes advantage of an interesting property of 2's complement. 2's complement is the way that computers usually represent positive and negative integers. In the 2's complement representation, the negative version of a number is actually the bitwise complement, and then you add 1. If you look at these two results, the only bit that they share is actually the least significant one. So wherever the first one is from the left, that's the only one bit that they share. If we want to extract that least significant bit, then all we've got to do is say x and negative x. This next bit hack is called a masked copy. We have three operands, A, B, and a mask called M. We want to copy bits from B into the variable A, wherever there is a 1 bit in the mask. And then the rest of the bits in the A variable should remain unchanged. The way that we do this is we perform two little expressions and we OR them together. So the first expression that we'll perform is B and the mask. And what this is going to do is select all of the bits from B that correspond to 1s in the mask. And then we OR that with A and not the mask. Select all of the bits from A that don't correspond to 1s in the mask. And when we combine those two results together with an OR, what we end up with is a masked copy from B over to A. The next bit hack is swapping two bits. Let's say that we have an integer variable, x, and then we've got two indices, a and b. The objective is to swap the bits at the indexes a and b in x. One clever way of doing this, the first thing that we do, we XOR those two bits together to produce p, an intermediate variable. And then we AND that with 1. That's going to give us a 1 if the two bits in X are different, and it's going to give us a 0 if the two bits were the same. If the two bits need to be flipped, in other words, if P just here is a 1, then what we can do is just shift P over to the correct indices and flip the bits by XORing with P. And if P is 0, then we don't have to change anything because this same XOR here will have no effect at all. We've effectively swapped the bits. This next bit hack is called a population count. This one comes from Brian Kernighan. We want to count the number of bits that are set to 1. What we do is perform an interesting operation. X equals X and X minus 1. It zeros the lowest 1 bit. So in order to compute the population count, all we have to do is set up a little loop and then keep performing this expression until x equals 0. Then we return the number of times that the loop iterated. And that is our population count. This next bit hack I call counting bit islands or counting bit blocks. If you look at an integer in binary, you'll see that it's made up of islands of ones, and they're separated by zeros. We want to count the number of islands. One way that we can do this is this interesting expression right here. It looks fairly complicated, but let's break it down a little bit. If we look at the value that's inside the population count call, then what you'll see is x XOR x shifted to the right one space. And if you have a bit of a look at what this achieves, XOR, if you remember, computes a mask and it puts a 1 wherever the two values were not equal. So if we XOR x with itself shifted down one space, then the mask that we're going to get will reflect where the zeros and ones change in the variable x. And then if we perform a population count, we'll almost have the number of islands that we're looking for. X XOR x shifted 1 to the right actually counts not only the changes from 1 to 0, but also the changes from 0 back to 1 again. We only want half of that count. And the final part just here, you'll see at the start of the expression, all that's going to do is ensure that we count the first bit island. The population count and the little XOR and shift expression up there is actually not going to count the very first island if our integer begins with ones. So in addition to performing the little population count there and the shift and the XOR and the divide by 2, we've also got to remember to count that first island if the integer starts with ones. And that's why we see at the very beginning, x and 1. This next bit hack is called a bit scan forwards. Our objective here is to find the index of the lowest set bit. That's the lowest one coming in from the right hand side. It's zero based counting, so the rightmost position is position 0. The other thing that I want to mention about bit scan forwards, if you're using an x86 CPU, your Intels and AMDs, they actually have an instruction called bit scan forwards or BSF. But just for interest's sake, and for anybody that's programming on devices that don't have an inbuilt bit scan forwards instruction, yeah, we'll present this little bit hack just here. There's a lot of different ways to do this. One of the ways I think is really interesting and clever is this one right here. For a bit scan forwards, one of the things we have to decide is what to return if there's no bits set. At the top of this, I've just returned -1 for that particular instance. The next line should look pretty familiar. X equals x and -x. That's actually going to isolate the lowest bit in x. And the next thing that we have is an interesting bunch of if statements. And there's also ways to do this with branchless programming, but just for clarity, I've presented these as if statements just here. X and then we've got some sort of a mask just here, does not equal 0. And what that's going to do is mask out everything in X except for the upper 16 bits. So if the 1 appears in the upper 16 bits, then we add 16 to our count. And then the next masks are similar, but now we've masked bytes, or 8 bits at a time. And once again, if X and our little mask does not equal 0, then we can plus onto the count 8. And then we've got masks of 4 bits each. If X and a mask of 4 bits does not equal 0, then we know that our little bit, wherever it is in the integer, we've got to add on 4 to our count. And then we mask off every 2 bits. And then every second bit. By the time we've performed these 5 little operations and added to these counts here by specifying the masks, the end result will be the index of our isolated bit, the index of the rightmost bit in X. Which brings us to our final bit hack, the most complicated of all. This one is called lexicographic order on the Stanford website, and it's called co-lexicographic order or colex in other sources. I will leave links down below so that you can read up on these things, but whatever it's called, this is what we're doing. Say we have a string of binary. There's some certain number of bits set in that string. So this one right here has 3 bits set. What we want to do is generate the next integer above this one that also has 3 bits set. What we're really doing here is just iterating through combinations in order from 8. We're choosing 3 bits, and we want to be able to list those in order. What this bit hack does is when we give it a bit string, it computes the next bit string above with the same number of 1 bits set. It's very, very common that we've got to iterate through all of the combinations of various different objects. And this little trick will give you all of those combinations in order with about 2 lines of code. Absolutely amazing stuff. Here it is just here. Alright, let's break this down and see what it means. We're going to use the bit scan forwards function, and I'll just put up on the screen another version. This is a version without the bit scan forwards function, so this will be slower because it uses division. But at any rate, we'll just assume that we have the bit scan forwards. If we look at the first line of code here, we have the expression t equals x or x minus 1. And this might look a little bit familiar because this is actually the trailing zeros bit hack from earlier. Convert any trailing zeros in x to 1s and store that result as t. So t is going to be the same as x, except any of the zeros on the right hand side will be 1s. And moving on to the second line, the first thing that we see here is t plus 1. T begins with just a block of 1s. If we add 1 to that, what's going to happen is that a 1 is going to pop into the first available 0 spot in X. Not including any of the trailing zeros. This is good. This is the one that we want to increment, but we still have to worry about any of the 1s that need to be reset over on the right-hand side. So whenever we're counting up in this lexicographic order, one of the 1s will increment, it'll shift over to the left, and any 1s below that reset. They get shifted to the right as far as they can go. That's just what ends up happening when you count up in this way. So far, we've figured out how to increment that little 1. The only thing that we've got to do now is figure out which ones have to be reset over to the right. If we look at the next section here, we see something really interesting. We've got not t and negative not t minus 1. First of all, not t and negative not t. Well, that might look a little bit familiar because if we just get rid of the nots here for a second, what we'll see is t and negative t, which is one of the bit hacks that we've already looked at. This is the bit hack which isolates the lowest 1 bit. Now, because of the nots, we'll actually end up isolating the lowest 0 bit, but the position of that 0 will be represented by a single 1. If we remember back to what t actually is, this single 1 bit just here will be in the lowest non-trailing 0 position in X. So wherever the first 0 was in X, that wasn't a trailing 0. And then when we subtract 1 from that, we end up with this mask of 1s up to, but not including, the position of that 0, that non-trailing 0 in X. And we know that some of the 1s in this mask are going to be the ones that reset over to the right-hand side of X, but probably not all of them have to reset. There's probably too many 1s in this mask. And the number of 1s that we have to remove from this mask is the same as the number of trailing 0s that there were in the original X. We don't want to reset any of the 0s in X. All we're really concerned about here is resetting the 1s. So however many trailing 0s there were in the original X, we can actually discard all of those from the mask just by shifting to the right. So if we do a bit scan forwards and get the index of that 1, what we've got is the count of trailing 0s. And that's almost the amount of 1s that we want to remove from our little mask, except one of our 1s actually incremented. It shifted over to the left. So we actually want to remove one extra 1 from our little mask here. So you see this +1 here on the end of our bit scan forwards. So if we shift our mask to the right, what we'll have is our little reset 1s over here on the right hand side. And then all we've got to do is OR that result with the incremented 1 from before, and hey presto, we've got ourselves the next bit permutation in lexicographic order. Can you believe it? And that, my friends, is bit hacks. Good stuff. I'll be putting up the sources for the Patreons as well as the Blender files that I use to make these 3D animations. And the other thing that I want to say is fairly soon we'll be updating the store, so you can get Creel official merchandise below if you like. The original merch that's still for sale now will be switched out for some new stuff coming soon. So if you do want to get this original stuff, just snap it up now. Otherwise, hopefully we'll have some new merch coming very soon. Anyway, thank you very much for watching, and I want you to have a really good day. Or you can subscribe and like too if you want, or leave a comment down below. Have a good one, mates. Have a good one.